Hello. Today we're going to present our senior project, which is on F-prime embedded systems. My name is Joseph Amawing. I'm here with Ruben Rangel, and our advisors are Dr. Ali and Dr. Formicola.
What is F-prime? F-prime is a flight-proven, multi-platform, open-source flight software framework. It was developed at JPL and successfully deployed on several space applications. F-prime comprises several elements, like a C++ framework that provides core capabilities like message queues and threads. It has tools for components, connections, and it's able to automatically generate code. It has a growing collection of components that provide standard flight software behavior, like telemetry, ground interface, time, health, assertions, and fatal events, etc. It has also some different features like reusability, high performance, rapid deployment, adaptability, portability, and analyzability. F-prime is tailored but not limited to small-scale spaceflight systems like CubeSats, SmallSats, and different space instruments. It's able to run on several operating systems like Linux, Mac OS, and VxWorks. It also runs on a wide range of hardware platforms. The importance of F-prime is the development of flight software is challenging. Some of these challenges include small budgets, inadequate resources, under-specified and changing requirements, and compressed schedules. Some of the solutions for these challenges include developing flight software from scratch. However, that's too expensive and can compromise the quality. Another solution is to adapt flight software from a previous mission. However, that's not ideal since it requires a complete re-engineering of the flight software. So the best solution is to use a multi-mission flight software framework. The goals of our project include install F-prime to run on FPGA and demonstrate the capabilities of FPGA. To, uh, to do this, we'll be building a new component, run tests, and benchmark different types of hardware. We're gonna collect performance measurements and benchmark it against the Raspberry Pi. One piece of hardware that we're gonna be using is the Pink C1 board. It has a 650 megahertz dual-core Cortex A9 processor and 512 megabytes of DDR3 RAM. It's compatible with Python, C, C++, and Verilog. Mm, This, um, this platform uses Python language and library that makes it easier to design hardware. It makes it easier for software developers to design hardware, and for hardware developers, provides an easy software interface.
So the other piece of hardware that we selected is the Raspberry Pi 4. Now this has a 1.5 gigahertz quad-core processor, and it also has 4 gigabytes of RAM. It also runs on the Raspbian OS, which is a Debian-based Linux distribution. So after we installed F-prime, the first thing that we ran through was the math component tutorial, which is found on GitHub. And this basically runs us through the process of creating our own F-prime application or component. So by doing this, we were able to add 2 new components and 2 new ports. The components we added were math sender and math receiver. Math sender sends a command to perform an operation, and math receiver is used to set factor for that operation. The ports that we added were the math op port and the math result port. The math op port is used to pass the invocation of an operation from math sender to math receiver, and the math result port is used to pass the result of the operation from math receiver to math sender. So after we ran through that, the next thing we wanted to do is we wanted to launch the ground data system, or GDS. So GDS is a browser-based graphical user interface that allows users to interact with the embedded system. This can be used to issue commands as well as to check events and channels. Using the GUI is not necessarily required, as GDS can also be used on the command line interface, also known as GDS CLI, and we'll actually see that a bit later. So on the right, we can see the GUI that we opened using the Raspberry Pi 4. Here we're seeing interacting with the math component that we created earlier from the tutorial. So the next thing I want to talk about is the command line interface, which I mentioned earlier. This is also known as F prime CLI. So at the start of our project, we actually used a virtual machine to familiarize ourselves with F prime. So what we see here is actually us running GDS CLI on this virtual machine. In order to do this, we had 3 terminals. The first terminal was used to actually open GDS. The second terminal was used for viewing the logs. And the third terminal was used to send commands. After we got a bit more experience with this, we were able to compile some of the commands that we used into a shell script. So the first part of the script follows the scripts and sequences from the tutorial that is found on the GitHub repository. This includes commands for addition, setting the factors, and saving the parameters. The next part of the script tests other parts that we use in the component. So this includes operations such as subtraction, multiplication, and division. We also wanted to test some other cases with numbers such as numbers with decimals and negative numbers. Overall, we actually ended up with 26 commands for this script. So once we finished that script, we wanted to benchmark our hardware performance. For benchmarking, we ended up using the star command from the systat package, and this allowed us to view the CPU usage. We ran this at the same time as the shell script so that we can see how it would affect the CPU usage. We were able to output all of the statistics into a separate file. We ran benchmarks on both the Pink Z1 and the Raspberry Pi 4, and we were also able to compare these results with the results that we got on the virtual machine. So seen here are the results that we got. In blue, you can see the Raspberry Pi 4. In orange, you can see the performance of the Pink Z1. And in gray, you can see the performance of the virtual machine, which ran the Ryzen 5900X, which we had 1 CPU for. So for results, we found that the fastest was the virtual machine, which again was running on 1 CPU of the Ryzen 5900X, and this took about 8 seconds. The slowest was the Pink Z1, which took about 44 seconds. The Raspberry Pi 4 took about 11 seconds. We also found that the Raspberry Pi 4 had the lowest CPU usage with the virtual machine, while the virtual machine actually had the highest CPU usage. I actually found this to be a bit interesting considering that the virtual machine was running on a much newer and much faster processor. So we've essentially concluded that the math component operations are faster when we're using a faster processor, and generally the amount of CPU usage is dependent on the number of cores used, and these results are pretty expected. For the math component, we concluded that the Raspberry Pi 4 performed better than the Pink Z1 as it has a faster processor and also has more cores. So just some of the other future work that we were looking at doing, we also want to build our new component. As I mentioned earlier, from the math component tutorial, we learned how to create our new component, and we hope to implement that and try and create something completely new on our own. We also hope to complete the GPS tutorial, which is also found in the FRAM GitHub. Of course, for any new component we create, we want to run new benchmarks, and we also want to attempt implementing other benchmarking methods. And here are just a couple of the resources that we used. Thank you.